All right, so we're going to take a look at some of the practice problems that I put together for AP. There's a sheet in which we had 3 different practice problems for static equilibrium. Most people seem to do pretty well with question number 1. That was something that was a simpler version of what we did in class. Question 2, people had a little bit of trouble with, but they managed to work that out pretty well. But I know that I've gotten quite a few requests to take a look at question 3. Question 3 has the following. We have a building, and we've been tasked with hanging a sign. We're going to have a rod that comes off of the sign, or off of the wall, I should say, and it hangs a sign right here. There. It's a physics story. We've also got a wire that is helping support that sign. All right. Here's the thing. I'm going to mark these out. So we're going to say that the rod has a mass, capital M, being equal to, let's see, 6.4 kilograms. It is also 57 centimeters long. I give some further dimensions that this is 26. Yeah, 26.6 centimeters. Great. And that the sign has a mass of 2.7 kilograms. I have a couple of questions. First and foremost, what is the force of tension in the wire that runs from here to here, helping hold the sign up? The other 2 questions deal with the force of me bolting the rod into the wall over here. All right. Let's take this in the order that it's given. I'm looking for the force of tension initially. We know that we're dealing with static equilibrium, which means what we really need is sum of forces to come up to 0, and we need the sum of torques to also come up to 0. As we've hopefully seen up to this point, usually when you're dealing with a full static equilibrium problem, we want to go through and we want to take a look at the sum of torques first because it gives us some opportunities. Of the things we don't know the force of tension and we don't know the force here at the wall. So if I set my center of rotation over here at the wall and use sum of torques, I will not have a lever arm for this unknown force, which means it will disappear from my calculations and I don't have to worry about it, which is a smart thing to do. Now, you don't have to do it that way, but it is the way that is going to get you the least amount of work and get you the force of tension the fastest. All right, the key things that we want to draw out. We have a force here that points off in some unknown direction because we know almost nothing about this force over here. We've got a force of gravity acting on the rod, right in the center of the rod, and we have a force of gravity acting on the sign, which is in turn pulling on the rod right here on the outer edge. We have a force of tension that is now pointed up at an angle like this, but I do not give you the angle. All right? Well, if this is 26.6 and if this is 57, then we can do a little bit of trigonometry where, let's see, tangent is TOA, so that's opposite over adjacent. So if I do 26.6 divided by 57, and then I do the inverse tangent of that, I should end up with this angle here, which, if I've done this correctly, is about 25 degrees. Inverse tangent, TOA, opposite over adjacent. Sounds good. All right. Let's go through and do our sum of torques, with this being my center of rotation. All right, sum of torques. Now, I've kind of colored or drawn these out with the different colors, but I'm going to stop doing that. You'll see why here in just a minute, because we're going to have to deal with some components on our forces. And so I'm not actually going to maintain the color code on this. I'm going to go back to our regular color code. I like to move outwards away from the center of rotation. Over here we have the unknown force from the wall. It's a force, but its lever arm is 0 meters, and we don't actually know the angle between them, but it doesn't actually matter because since the lever arm is 0, it disappears. That's that thing I was saying about choose your center of rotation wisely. Next one over, moving outward. I have the force of gravity on the rod itself. Now the force of gravity, let's grab the green one, is going to be the mass, 6.4 kilograms, times the acceleration due to gravity, 9.81. That's my force, mg. For it to be a torque, I need the lever arm as well, which is from here out to here, which is half the length. The full length is 57 centimeters. I could have made this easier. 0.57 meters divided by 2. I'm feeling lazy, so I'm going to put that into the calculator. My lever arm is 0.285. It's about 28.57 meters. This is in meters. And sine of the angle between them, my lever arm is straight to the right, and my force is straight down, so the angle between them is 90 degrees. Sine of 90 degrees is 1. And the final thing is, and you'll notice that I left this blank, I have to choose directions. Now, the best way to do this is ignore the other forces. Ask yourself, if this is the only force, and here's my center of rotation, it would pull this down. The whole thing would swing this way, which is clockwise, which by convention is negative. I will once again remind you that you do not have to use the convention. If on the exam or anything that you've got, if you want to make this positive, that is perfectly fine. Just remember, when you find something that then makes it go the other way, you must keep track of positives and negatives, but I do not care which way you declare to be positive. I will continue to use the convention just so we have kind of a common ground that we're constantly going with. I continue moving out, and I'm going to come to, let's go ahead and do the weight of the sine. It's pulling down on the rod. So I'm going to do minus, because it's going to make the red, the sine here is going to make it swing clockwise, so that's minus. The force is 2.7 kilograms times 9.81, that's mg, times the lever arm, which is 57 centimeters, 0.57 meters, times sine of the angle between them. Force is straight down, lever arm is straight to the right, so that's 90, sine 90 again. I'm not going to write it, it's just 1. So this is my torque. Here's where things get a little bit more complicated. The last force that is acting on this is the tension. Now, I want you to imagine, ignore the other ones. If I were pulling up like this, it would pull the end of the rod up and go around like this. This is counterclockwise, so I'm making this a positive. All right, we don't know the force of tension. So that's Ft. We know that the lever arm is 0.57 meters. And here's where it gets a little bit tricky. That's why I've thrown this one in, because it's a little more complicated. I'm going to draw this out. I have my lever arm that goes straight from the center of rotation out to where the force is being applied. That's D. I also have the force that goes up and to the left like this. This is my force. I want the angle between these two, so I'm going to put them near each other. Oh no, stop that. We did this before in work. We are not adding the vectors, we're finding how they point with respect to each other. So, put them basically side by side like this, and this is the angle between them. One of them points right, and one of them points up and to the left. This is theta between. This is 25 degrees, and the full arc here is 180 degrees, which means theta between comes up to, what is that, 155? 155 degrees. That being said, I don't recommend this, but many times it will work out this way. The sine of 25 degrees, if you blindly put in an angle that you found, is 0.422, and the sine of 155 degrees is the same thing. I do want to point this out, just so you're aware of it. You can use the wrong angle and sometimes end up with the right answer. That does not mean it will always work. Pay close attention. I can promise you that the only way to be guaranteed that you get the torque, the correct torque, is to not grab whatever angle happens to show up in the problem, but draw out your lever arm and the force and find the angle between them. That will get you the torque. I've watched many students just go, it gave me 60 degrees, so I'll put 60 degrees in there and get profoundly the wrong answer. Draw these things out so you know exactly what you're putting in. Here we need sine of 155 degrees, or if you prefer radians, you're welcome to radian it up or whatever. Since this is my sum of torques, all of this must be equal to 0. Sorry that I'm kind of crammed there, but I can go through and everything except for ft is numbers that I happen to know. So 6.4 times 9.81 times 0.285 plus 2.7 times 9.81 times 0.57. I end up with the following. Hey, look at that. If I were to write this out, these are the negatives, so I'm going to have 0 equals negative 32.99. Let's call that 33. Nice even number. So negative 33, these are all Newton meters, plus Ft times 0.57 times sine of 155. I end up with 0.241, 0.2408 if you'd like, but I'm going to add 33 Newton meters over to the other side. This has units of meters, by the way. I'm being kind of lazy on that, but I'm going to take 33 divided by that value. And I end up with, keeping all the significant figures and all of that, I've come up with about 136.99, which is 137 newtons. Remember, this has units of meters, so when I divide Newton meters by meters, I will end up with newtons. The force of tension is 137 newtons. That's part 1. Part 2 and 3. We want the force at the wall. I'm going to tell you this. In the setup of the problem that I've got, this force will actually point up and to the right. You may not realize that, but one of the things that you do need to realize in order to solve this, for part 2, we need our sum of forces to come up to 0. And this problem is specifically designed. We now have a force of tension that goes up and is equal to 137 newtons at 25 degrees. Well, if I want to be thorough, it's actually at 155 degrees because we always give the angle measurement with respect to the positive x-axis. But the important thing is I've got an x component, ftx, and I've got a y component, fty. I can find these. In fact, let's go ahead and do that. So I'm going to do 137 times the y component. That's going to be the opposite side, so sine of 25. This one is equal to, looks like, 57.9 newtons. And over here, cosine of 25, and then multiply that by 137. If I've done this correctly, this comes up to 124.2. We could just call that 124 for 3 significant figures. When I do my sum of forces in the x, let's do the x first. Sum of forces in the x. That's going to be the unknown normal force from the wall. It's a physical contact force. We'll call it force of the wall in the x. That one is either positive or negative, though I've got an idea that it's got to be positive. It's going to be pointed out to the right. The only other force that I have in the x, going back up here, I have the sine straight down, I have the rod straight down, and I have the tension that is up and to the left. So the tension's really the only thing here that we know of that has an x component. That's also a clue that this has to have an x component, because again, for statics, this has to come up to 0. So I'm going to do minus ftx, and that equals 0. Well, the force of the wall in the x minus 124.2 newtons needs to equal 0, and therefore the x component of the wall, hey, look at that, is 124.2 newtons. We found the x component. Now we're going to do the same thing in the y, sum of forces in the y. This one's going to be a little bit trickier. I've got, going downward, let's see. Well, first off, let's say that we've got the force of the wall in the y. There might not actually be a force in the y direction from the wall. It might be that these are going to cancel out perfectly, and we end up with finding that the normal force, or the wall force, in the y is equal to 0. That is a thing that can happen. We could design this where this doesn't have to be bolted in at all. It can just slide up against it and sit there. That's not usually how you design them in real life, but it is something that we could easily do. In fact, a lot of times you put the wire there to help reduce the force on this. You might take it all the way down to 0. We're not going to find that in this one. That's okay. Minus the mass of the sign times the acceleration due to gravity. This is the weight of the, no, sorry, not the sign, the rod. Minus the weight of the sign, and plus the force of tension in the y. Why is it plus? Because the force of tension in the y is up. All of this must come up to 0. Force of the wall in the y minus 6.4 times 9.81 minus 2.7 times 9.81 plus, what did we say the other one was? 57 something? 57.9. 57.9 equals 0. We can now solve for the force of the wall in the y. Let's see, 6.4 plus 2.7 times 9.81, and then minus 57.9. I'm doing a bit of math in my head, but what you should come up with is the force in the y is 31.37. We'll call that 31.4 newtons. Neither of these are my answer, but they are the components of my answer. I have an x component that's 124.2. X component, 124.2. And I have a y component, this is stuff that we did last semester, 31.4 newtons. I can now find the total force from the wall using Pythagorean theorem. 124.2 x squared plus 31.4 x squared, square root, and we end up with the force of the wall 128.1, 128 sounds good, newtons. And finally I ask, what direction does the force from part 2 point in? Theta. Theta in this case will be the inverse tangent. TOA is opposite over adjacent, so I'm going to do 31.4 divided by 124.2. And I will do the inverse tangent of that. Make certain your calculator is in degrees if you want this in degrees. I guess you could solve this in radians if you want. It's whatever you'd like. 14.188, let's call it 14.2 degrees. It points mostly to the right, but slightly up. These are the answers that you should end up with, as long as I haven't made any math errors, but I'm pretty certain we're in good shape. It also sounds pretty reasonable. All right.